Okay, so this is 12, 15, 14. And I gave you CH4, which we did together on our own. And you know that this is one carbon atom and 4 hydrogens. And furthermore, you know that carbon has how many valence electrons? 4. 4 sites for attachment. I saw a few people who put 6 on there because they're looking at the total number of electrons. And remember, you don't want to do that. You only want to do valence. So make sure you're not making that mistake. And then hydrogen has 1 lonely valence electron. Single hydrogen is seeking electron to share for possible long-term relationship. So, whoopsie. Hydrogen goes right in there. And, oops, I should just move that whole thing out. Okay. Once you've got a pair of electrons that are shared, you can replace those with dashed lines. So your final Lewis structure, and I'm not sure if we addressed that as thoroughly on Friday. Your final Lewis structure for this should, well, it should look like that. So you've got a carbon surrounded by 4 hydrogens. It's pretty easy breezy. And I think most of you did pretty well on that. As I said, I'm not sure we talked in any kind of depth about replacing those dots with lines. So if you didn't get to that, that's fine. So I think I would say greater than 90% of you got this correct. Okay. So let's go to H2O next. Again, we're working with something that's got hydrogen. And so that's nice and easy because there's really only one way you can attach hydrogens. A few words of caution, a few things I am noticing some of you doing before we go on to water. So cut. I saw a few people who want to put their hydrogens sideways so that the Lewis dot is still at the top. Please don't do that. Just go ahead and write it as though you're reading it because that could be confused with iodine. So don't do that. Don't try to turn letters on their side to get the top to line up. Because remember, those electron dots that we put around the 4 corners or the 4 sides of the symbol, they aren't reality. They're a representation of reality. So, but the dots are on that side. I have to. No, you don't. No, you don't. It's okay. Let go of that. It's all right. Oops. And the other thing is, don't put your lines horizontally. Just connect them so it's clear that you're connecting. As visual representations go, that's a challenge. So I'm going to model all that, but I want to explicitly state that you should do that. Okay, so great. We've got methane here, and we'll go ahead and come back to doing our water. Let's get rid of this guy. Cut. Okay, so we know that we've got 1 oxygen, which looks something, I should be using this, something like that. And we have 2 hydrogens, which looks something like that. So this is seeming pretty easy and pretty obvious, yes? Okay. There are some subtleties that we'll pick up later, but, obviously we're going to have that, right? Now, we have not talked about molecular shape yet. We will extensively. If you have 2 hydrogens, they're both essentially at their core, a big proton. Those protons want to be as far from one another as possible. Well, guess what? These electrons, these are called, well, let's ask this. Are they shared with anybody? No. They are therefore called unshared pairs. Those are called unshared pairs. I can't remember if we addressed that on Friday or not yet. Okay, so you'll want to make a note of that. That's really important. Those are unshared pairs. And we're most concerned with those when they're on the central atom. We're going to start to talk about which is the central atom and how you figure that out too. Okay. So, let me get rid of my little circles there, because they look like some kind of aliens. Those unshared pairs also want to be as far apart as possible. We will build three-dimensional models of this, and you'll see how they get as far apart as possible. Water is not arranged in a straight line because those unshared pairs push the hydrogens. And so while as a two-dimensional representation of something that's actually four-dimensional, an argument can be made that that's correct. Because of that change in geometry, water is traditionally shown in the following way. Let me get rid of these guys. Nope, that's not what I want to get rid of. Cut. That was a lusty sneeze. Let me move all this up. So because of that change in structure, water is traditionally shown as okay. Yeah. Now, like I said, this is a two-dimensional representation of something that's three-dimensional. When you see them, when you build a model of water, you're going to understand why, on some level, it doesn't matter. But what does matter is knowing that water is actually bent, and we'll talk much more about that. That's where we get the Mickey Mouse, little Mickey. And if you think about Mickey looking like that, you know, there's a big island of negativity. Remember, water's polar. Okay, let's go to the next one that you should have been pretty easily able to do. So the next one was, this is called carbon tetrachloride. It's 1 carbon and 4 chlorines, and it is nasty, nasty, toxic, carcinogenic. It'll kill you fast, it'll kill you slow, it'll just kill you. When I was in college, we used this in our kill jars in biology. Carbon tet. It was also at one time used by draftspeople to clean their tools because it gets graphite off of things really nicely. There are long-term and short-term risks to carbon tet exposure. It's not nice stuff at all. It's a nasty organic chemical. So, that being said, what do we have? Well, again, we've got 1 carbon. Let me use my better dots. And we've got 4 chlorines. And chlorines, if you remember, look like that. Well, this seems like jigsaw puzzle stuff, doesn't it? Because you can just take chlorine and basically plug it in, whoops, repeatedly. And I will plug in chlorine. And of course I have some cheater tools at my disposal here. Yeah, let's not do that just yet. Okay, so that's what our sort of base would look like. Now, every place that there are shared electrons, we can replace them with a what? A line. So what this ends up as is we'll get rid of these. It ends up looking like that. Oop. I'm going to fix this in a second. Oops. Oops. Okay, so that's what our final structure for carbon tat should look like. You do have to show all of these, what are those called? Unshared pairs. You do have to show those even on the outer atoms, though they don't influence shape. And we will talk a whole lot more about what influences shape and what doesn't. But really, we're from a molecular geometry perspective, which we're going to get into, the unshared pairs matter most on the central. But for a correct Lewis structure, you have to show all the unshared pairs on the outside. Okay, how many of you got pretty close to that? Okay, we're going downhill here. So we had, with methane, CH4, everybody's like, yeah, I got that, this is good. And with water, you know, slightly smaller percentage said, yeah, I got it. And we're going downhill a little bit. These are a little bit more complicated. The fact that this is not hydrogen and doesn't just have, you know, one little electron set confuses some people, but it really is bonding the same way hydrogen is. It's chlorine by itself has got one place where it can attach to anything else. Doesn't matter what side we draw it on, but so does hydrogen. So it's the same principle. Okay, now, how many of you felt totally comfortable and you think you have SO2 right? I'm going to tell you, I bet none of you have it right. Because the SO2 drawing involves something we haven't talked about yet. Double bonds. Bingo. So let's go on to SO2. All right. We have our sulfur. I'll get to there, right? Excellent. The first thing is pretty easy because oxygen has this nice little site for attachment here. Sulfur has one there. It's like a jigsaw puzzle. So we just go fix those. Oops. But there's a problem, because oxygen had those other electrons. What do you do with those? Here's one rule to remember, to make a note of. When you are done with a Lewis structure, you can never, ever, 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 never have a single electron hanging out by itself. No single electrons hanging out by themselves. If you hand in a Lewis structure to me and it's got a single electron hanging out all by itself someplace, it's wrong. Just totally, it's wrong. Down in flames. MAP gas powered. It's ugly. Okay, you can't have that. They don't do that. So what the heck do they do? Well, it turns out what happens is that we get a double bond. Those two electrons come together and they form a double bond. And now you're saying to me and to yourself, well, wait a minute, wait. This one was over on this oxygen and this one was over on that oxygen. They can't form one double bond between a sulfur and an oxygen. That's not okay. That can't happen. Come on. Anybody having some cognitive dissonance with that? Does that bother anyone? Good. Good. Excellent. I like to bother you. They do. Remember, what we're talking about here are those tennis balls with those clouds of cotton candy, and they're merging their clouds of cotton candy. So the electrons, they aren't where they started off. And we're going to come up with a mathematical formula for figuring out when double bonds exist. Let me pause. Okay, so the next question is, well, how come you put the double bond there? Couldn't it be here? Hold that thought. Okay, so the multiple bonds thing. That's the first thing we ran into with SO2, is that sometimes atoms will share more than one electron, and that leads to a multiple bond. We talked about this with the rubber bands. So you know that we can have a double bond, we can have a triple bond. I don't know of anything that does a quadruple bond. I don't know that it's possible. Maybe somewhere, but I don't know of anything in our galaxy. Feel free to write to a chemist and ask me if, ask them if that's true. But I don't know of anything that quad bonds. But double and triple bonds are pretty common, especially with carbons. And so all we're talking about there is something that is sharing more than one pair of electrons. Okay, and either 2 or 3. We demonstrated using the rubber bands. Multiple bonds tend to be shorter. They tend to be stronger. They have more energy. We talked about it with MAP gas. That MAP gas has got a triple bond in there, which means there's more boom for your buck, which means you better watch out if you're firing off potatoes. So the SO2 showed us a situation where we've got something that is sharing more than one pair of electrons. Okay, fantastic. Well, the next question is, why there? So we have lots of substances that have double bonds or triple bonds that could exist in more than one location. So could that bond exist in more than one location? Yeah, you bet. As was so aptly pointed out by one of your fellows, well, why isn't it over there? That gets us to our next point, which is what are called resonance structures. Okay. So a resonance structure is something that's necessitated when there is a molecule. Oh, yeah, wait, I have a problem. Oh, you know what? I don't have a problem with that. Let's go back to SO2, and we'll look at where I screwed up, because you'll screw up in the same place, I'm quite sure. So it's good to know where the pitfalls are. When you think you're done with a Lewis structure, you got to do some counting. So if we go back and look at carbon tetrachloride, carbon tet, when we look at the final structure for carbon tet, we can count up the electrons that are surrounding every single atom in that structure and say, do they satisfy octet? Does everybody have 8? And here we're not dealing with any of the weirdos. We're not dealing with hydrogen, which shares to get to 2. We're not dealing with things like boron that go to 6, or fluorine that can absorb more than that. So let's, we'll count these and check them off as we go. This chlorine, 1, 2, 3, 4, 5, 6, 7, 8. Remember that line represents 2. Is that chlorine happy? Yes. This one, 2, 4, 6, 8, happy. 2, 4, 6, 8, happy. 2, 4, 6, 8, happy. Chlorine, 2, 4, 6, 8, happy. Everybody's happy. Everybody's good. Well, let's go back to the sulfur that I screwed up, and let's do that same little counting. So 2, 4, 6, 8, happy. 2, 4, 6, 8, 10. We got a problem. We got a problem here. We got a problem. 2, 4, 6. We got a problem here. We have a problem. So, what ends up happening here, that's right, we get 2 electrons. Yeah, that's how that happens. Okay, hold on. Let me Let me back up a second. Let me shrink this. The other thing I'm going to tell you, and this is something that physics kids hear a lot, and you'll hear a lot next year if you take physics. It's okay to go down a blind alley as long as you figure out you're going down the blind alley. It's okay to get something wrong because walking back through the process really helps. Okay, so we've got, whoops, let me change that. I'm doing this live on recording, so I'm putting this out for all the world to see that I screw this up too. And we had 2 there, so except that we have those 2. So if we double bond that, and then we take this, yep, there we go. Okay, that's right. Yeah, you're really going to hate this. You're really going to hate this. Okay. Yeah, this incorporates pretty much all the things people hate. 2, 4, 6, 8, 2, 4, 6, 8. Yeah. Yeah, this incorporates all the things that people hate tremendously. And it still does require resonance. I forgot about that. So, we do get a double bond. We get a double bond right here. Let's do our counting. So this first oxygen, 2, 4, 6, 8, happy. Sulfur, 2, 4, 6, 8, happy. What happened is we took 2 of those electrons from the central sulfur. We moved them out to this end cap oxygen. 2, 4, 6, 8, happy. But that's not right! Yeah, it is, actually. Horribly enough. Yeah, it's awful. Everybody hates it, but you can't move stuff off the central out to another one. You can't just move electrons around randomly, because I drew those electron diagrams, and sulfur has 2 on the top and 2 on the bottom. No, it doesn't. It's one big fuzzy mass of cotton candy. They're sharing. They're trading. It's all kinds of crazy and lawless in there. So now we'll talk with this correct structure. We'll talk about resonance. So we'll get rid of these guys. Cut. Put them where they go. Cut. So why is that a single bond? Why isn't that a double bond? Why are the extra, I'm putting extra in sort of air quotes, why are those extra electrons on this oxygen not the other one? Well, this gets into a little bit of the history of what we know and what we think we knew about molecular structure. So, let's see, how can I do this? Paste. And then get rid of this. What we used to think, and by used to, and I'd have to check dates, but I know, like, within my lifetime and within my academic career, it was believed that these kind of molecules went around flipping their bonds, that the bond went back and forth, back and forth, back and forth, and the electrons went back and forth, like a little tennis game where the tennis ball is going from here to there, to here to there, to here to there, that these things flip-flopped. And what's understood now with better technology is that, in fact, they exist in this sort of hybrid condition. They exist in this condition that's sort of splitting the difference. So it's like having a bond and a half here and a bond and a half there. And a half a pair of electrons there and a half a pair of electrons there. Ugh. Terrible stuff. Well, how do we show that? Because we sure can't show that. So what we use is what's called a resonance structure. Resonance is the idea that something is vibrating back and forth between 2 states. It's a word we borrow from physics for this. So the way we show resonance, anytime that there's a situation, and this specifically happens with multiple bonds, where there is more than one location where that multiple bond could exist, we have to show all the possibilities. So we always bracket it, and we draw the first possibility. Okay. Close brackets. We put a double-headed arrow between the two brackets, or 3 brackets, or 4 brackets, or 5 brackets. We won't get up to more than 3 brackets. And then we draw the other possibility. And what we're saying here is, yeah, goes back and forth. Neither fish nor fowl. It exists in both these states. James, wake up. If you do not draw me brackets and arrows on something that has the possibility of resonance, it's wrong. Because you're not representing reality in the way that we represent it. So we will practice more that have resonance. And what I'm going to do now, I'm going to give you 2 tutorials on doing Lewis structures. Because like right now it doesn't seem too bad, I'm guessing. It's going to get terrible. We're wading into the swamp of quicksand, and like, what was the thing on Princess Bride? The fire sands or something? Yeah, it's that swamp we're marching into. There are giant rats and there are fire-breathing pits of quicksand. But it's okay, you'll survive, I promise. So the first thing you're going to do whenever you are doing a Lewis structure via this method is count the number of valence electrons you're starting off with. Okay? So how many valence electrons does carbon have? 4. How many valence electrons does oxygen have? 6. And we have 2 oxygens. So we have 4 plus 12. We have 16 valence electrons that we need to finish with. Okay, now, you know that everything wants 8 except a few weirdos. So boron's a weirdo, hydrogen's a weirdo. So basically what you're saying here is, how many electrons does everything want to have? Well, and this is, he calls it figuring out the octet electrons. So counting valence, counting octet. Well, for these, carbon wants 8, oxygen wants 8. So here we have 3 8s. We have 24, whoops, octet electrons that are divided. So now we subtract the valence electrons present from the octet electrons. So octet electrons minus valence electrons, 24 minus 16, we get 8. This is the number of electrons that will be shared. Okay? So what you've just figured out, well this is, I should write that there. 3 is our little subtraction problem. And this number is the number of shared electrons. And that's pretty intuitive if you think about it. Okay, we're bringing this many to the table, but we need to feel like we have this many. The difference is what we're going to end up sharing. Well, a single shared bond involves how many electrons? Hold up fingers. 2. So we take that number of shared electrons and we divide it by 2. And what that tells us is the number of bonds that we're going to see. We have the number of bonds that we should see in this structure. 8 divided by 2 is 4. So we're looking for 4 bonds. Well, we got carbon, we got oxygen. How many places for bonds are there? So we're going to go zoop, 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 zoop. Does that satisfy our bonds? Okay. Well, now the last thing we have to do is put our unshared pairs back in. So he has find the number of lone pair or non-bonding electrons, taking the number of shared electrons, and subtracting it from the number of valence electrons they started with. So we're going to have 8 unshared. So we have 16 was our valence electrons, 8 was our shared electrons. We're going to have 8 electrons that are not shared, that are unshared pairs. Well, carbon's octet is satisfied. If we look at carbon, does it feel like it's got 8? So carbon can't take any unshared pairs. 1, 2, 3, 4. Well, now that oxygen is satisfied. 5, 6, 7, 8. Hey, guess what? That's pretty slick. Let's try some more together. Okay, so this is from 39. Part A is too easy. If it's got 1 carbon and 4 fluorine, guess what? You've already done that today. That's just like carbon tetrachloride. That's carbon tetrafluoride. So B is 1 Se and 2 H. That's also pretty easy. Let's do C. Oh, the one thing we didn't talk about yet is figuring out what's in the middle. So here's a general rule of thumb for you. If you have 1 of something and 3 of something else, guess which is in the middle? The 1 of something. But the better rule for that is if you have carbon, carbon's always in the middle. If carbon's there, carbon's in the middle. Okay, I guess we'll work on these. Okay, so we'll wrap up tomorrow.
Yeah.